But is it enough? In 2000, the amount of power generated by wind turbines came out to be 2.53 gigawatts. But by 2020, this number rose to 113.43 gigawatts, a 45,000% increase. From a retrospect, that might look promising for a zero net future, but is it enough to avoid the catastrophes that climate change could potentially bring? Hey, my name is Joaquin Revello, and if you're new here, this channel is all about showing you the technologies that are going to help mitigate, if not solve, the climate crisis. As in all my videos, I bring actionable advice that, if brought to the market and if developed technologically, it could help mitigate, if not solve, climate change. So let's begin by looking at the engineering of wind turbines by getting really into the nitty-gritty. The high-level overview is that we have incoming wind that hits the surface of the wind turbine. In hitting the surface, the blades are able to rotate across an axis. You can think of the blades as a large wrench, and the wind is simply a hand that is pulling along the wrench as if it's a lever. Since the power from any spinning object is simply the torque times the rotational velocity, we see that by increasing the torque and by increasing the rotational velocity, we can get larger power produced. Thus, we either want to push harder on the axis of rotation or make the blades spin faster. Since torque is just the product of force and radius, or also known as the cross product, we see that we want the force applied to be maximum at an angle perpendicular to the blades. And this is because of what is known as the right-hand rule. So a stronger force can be found by having stronger winds hit the surface of the blade, which can be found using this equation. So when deciding where we want to put the wind turbine, we need to find a location that has dense air going as fast as possible. Other than force, we want to think of the length of the blade, with a longer blade leading to a stronger torque. Other than torque, we can increase the power generated by having faster rotation of the blades. Normal wind turbines rotate at roughly 7 to 12 revolutions per minute, and which is why they have a gearbox to essentially upshift that by upwards of 100 times. This thus allows for a higher RPM inside of the generator. While it might seem tempting to keep adding gearboxes to just make the shaft spin faster, unfortunately we cannot extract more power out of the initial torque of the rotation, and that is simply due to the conservation of power. In other words, since theoretically the power made from the turbine is equal to the power exiting the generator, we remember that more torque and more RPM leads to more power. Thus, we can reason that RPM and torque are inversely proportional, in order to maintain that the total power produced is a constant. We also see that we can convert torque into RPM, which we see in the formula H equals T times RPM divided by 2,252, where H is just horsepower. Engineers then find the optimal trade-off between torque and RPM in the generator. That leaves us with the question, though, of how air impacting the blade is able to be turned into rotational motion. Well, you first need to know that the purpose of the blade is to convert the kinetic energy of the incoming wind into rotational motion. Therefore, in a perfect world, the wind would have zero kinetic energy exiting the turbine, as all of the energy of the wind would be converted into moving the turbine. As you can probably tell, we know that this is impossible because the wind needs sufficient speed in order to exit the turbine and allow new wind to come and take its place. In fact, the maximum efficiency that we can possibly get is 59.3% of the total energy available. From this, modern wind panels tend to reach upwards of 70 to 80% of this limit, which leads to an overall wind turbine efficiency of roughly 41 to 47% of the total kinetic energy converted into rotational energy. There's also a lot of very interesting fluid mechanics going on behind the scenes, which I would strongly recommend you check out if you're interested. In fact, when I was doing the research and analysis of this content myself, I couldn't help but thinking of all the fluids mechanic research that I did while building a hybrid rocket engine for the CSSI. In fact, we can use the exact same equation when measuring rocket fluid flow mechanics to that of wind turbine mechanics. More specifically, the standard mass flow rate equation. As the wind mass into the turbine is equal to the wind mass out, and the kinetic energy is theoretically converted into rotational kinetic energy, we can derive the following equation for power. From this equation, we see that we want to make the area of the wind turbine as big as possible to get maximum power out. With this in mind, why did engineers end up choosing the 3-blade design rather than any other number of blades, it only makes logical sense that adding more blades actually increases the power out. While that is actually true, as we add more blades to the turbine, we are increasing both the cost of the overall wind turbine as well as the amount of stress placed on the pole of the turbine. Adding more blades does mean more surface of contact, leading to higher efficiency, but that increased efficiency decreases at a decreasing rate, getting a curve similar to that of a logarithm. In other words, we mathematically would be able to get 59.3% efficiency if we were to add an infinite amount of blades. However, the cost of adding more blades increases proportionally, as each additional blade costs the same as the previous one to manufacture and deploy. Thus, even if you had the economies of scale in order to keep manufacturing blades, there will be a point of blade manufacturing where the cost in extra blade does not compensate for the marginal increase in efficiency. But more on that in the economics section, which you definitely do not want to miss. So from this, the perfect ratio is found to be 3. Well, why not 2? And here's what's fascinating about this design, is that with 2 blades manufactured, you actually get faster rotational speeds than with 3. And this is because you are experiencing less drag. However, they are not ideal, as faster rotational speeds result in stronger centripetal forces, which put unneeded stress on the beams, as seen in the equation above, where omega is the rotational velocity. Thus, a stronger centripetal force will be pushing towards the center of the turbine, potentially damaging the blades. Not only is this force a large problem, but there is also an additional problem with the wind creating a back force attempting to push over the entire wind turbine to the ground. This would only become more dangerous and more expensive to the wind turbine tower as more blades are added, which put a lot of extra stress through the extra weight on the turbine support beams. Now, if we look at the actual wind turbine blade design themselves, at least the cross-sectional area, we see that the blade turbines have a design as seen on the screen. The purpose of this shape is similar to that of planes, which generate lift by having a higher pressure below the wing than above. Since the pressure is just the force over the area, higher pressure over the same area of the wing requires there to be a force that pushes the plane up, generating lift. However, unlike planes, the blades of the turbine are rotating. This rotation results in air looping around the wings and back to the front, resulting in a downwards force. Therefore, the turbines need to account for the velocity that is hitting the blade head on, as well as the velocity of the wind that loops back around, which is why you will see the blade be at an angle from the incoming wind. Because the perceived wind by the blade is both the vector sum of the incoming wind and the wind that looped back around. So you just need to add up the arrows and see that you essentially get a perceived wind that comes in at an angle. And what's most interesting about this design is that the rotational speed of the turbine changes based on the distance from the center. So you're going to get a different induced wind speed at different points along the blades. So you're essentially going to have different induced speeds at different points along the wings. Therefore, your angle of attack is actually going to change along the blades, with the twisting turbines accounting for this difference. Alright, now let's explore the economics of the wind turbine industry. Here, a simple modern turbine that produces 2 megawatts of power costs roughly $3.5 million to build. That is a setup cost of roughly $1.75 per kilowatts of power, compared to solar panels, which are at roughly $3 to $3.5 per watt, and nuclear at roughly 8.2 per watt. Therefore, to produce 1,000 megawatts of power, the setup costs of these turbines would be roughly $1.75 billion. This cost does not include anything after the production of the wind turbine, such as operation costs, transmission lines, line losses, and other costs like that, which are a key component to the net costs. In fact, if one adds up all of these costs, we see that the cost jumps to approximately $4 billion, which is roughly the same as building one nuclear power plant. Whether this energy is demanded or not, a wind turbine produces energy roughly 30% of the time. During low demand and without any viable alternatives to energy storage, this energy either is sold or goes to waste. This is somewhat of a problem because unlike coal or nuclear power plants, which can be shut on or off, a wind turbine's operating expenses remain the same regardless of the demand for power. These variations in wind speed can actually damage the gearbox, which is caused by the change in torque. Adding on to these wind speed variations, we see that energy generated by the turbine is not sent directly to the grid. Rather, it is coupled with the generators and then sent to the grid station. The reason for doing so is to compensate for the change in electricity, allowing for a more stable grid station. In other words, this power backup source is required for the stability of the grid station. Most European countries, such as Denmark and Germany, that use wind turbines are attempting to use them at their limit, with Denmark's grid relying on wind at just below 50%. To stabilize the grid, other sources of energy production are required to go alongside wind turbine. For instance, some of these countries are looking at pairing hydropower with wind energy to fulfill this purpose. Oftentimes during windy days, Denmark produced over 100% of their power needs, and thus relied on their power grid to send electricity out to other neighboring countries. With that in mind, let's explore transmission lines. Wind farms tend to be located in remote areas and thus naturally have longer power lines in order to reach the more high demand regions. This poses somewhat of a problem because as the transmission lines increase, the power loss through these transmission lines also increase. What is important to know now is that for the transmission of electricity, there is a need for costly transmission lines depending on the location of the turbine. Theoretically, turbines placed on top of mountains will have a higher power output because of faster wind speeds, but these come at the trade-off of longer lines with more expensive maintenance. In fact, a remote wind farm that is offshore requires even more expensive lines to transmit electricity than both on ground and overhead. However, this does come at the distinct advantage that the noise they produce does not affect nearby neighbors, which is actually a pretty large concern for the manufacturing of wind turbines. So instead of using coal power plants to accommodate for wind fluctuation, why isn't an alternative such as hydropower used instead? Looking briefly at the law here, in states such as California, hydropower is restricted due to the Endangered Species Act, as building hydropower tends to destroy ecosystems. Moreover, the state is negotiating with the BPA grid to meet the standards set by itself for the use of renewable energy. To meet the standards, the BPA is helping California with its demand for renewable energy and less dependency on hydropower. In the same way, many countries are reluctant to use wind power unless they have an agreement. Another question that arises here is whether or not there is an advantage and cost benefit of wind energy. Why is it being used, or why can't hydro energy / solar be used in its place? Well, the actual energy capacity of solar is smaller than that of wind energy, with solar producing roughly 500 watts, while the average wind turbine can produce 1 kilowatt. And here's where one of today's opportunities actually lie with creating wind turbine, and that is finding more novel solutions and applications to this technology. Some startups that are actually creating more novel solutions include New World Wind, Sea Twirl, and Vote. You can find all these startups in the links in that description below. Let's dig a little bit deeper to the economics aspect of this technology. In driving economic growth, actually wind turbines do play a role. For example, in the United States, the economic impacts of wind turbines is roughly 20 billion. This economic impact can actually be larger if the turbines are produced locally, which create more jobs. In fact, the US wind market supply has actually grown substantially over the past 20 years, as we'll soon see. In fact, there are more than 500 US manufacturing facilities specializing in wind components, such as blades, towers, and generators, as well as turbine assembly across the country. In fact, modern wind turbines are increasingly cost-effective, reliable, and have scaled up in size to multi-megawatt power ratings. Improved turbine performances have supported a robust wind industry, with the US wind turbine technology exports growing from 60 million in 2007 to over 100 million per year. In fact, supply chain management is key to wind turbine supply. The relationship between manufacturers and their component suppliers have become increasingly crucial and have come under increasing stress in the past 3 years, as soaring demand has required faster ramp-up times, larger investments, and greater agility to capture value in a rapid growing sector. In fact, supply chain issues have dictated delivery capabilities, product strategies, and pricing for every turbine supplier. Manufacturers have sought to create the most sustainable, competitive balance between a vertical integration of component supply and full component outsourcing to fit their turbine designs. In fact, a record 94 gigawatts of global wind demand is attributed to the two biggest markets, China and the US, which strained the wind supply chain in 2020. COVID-19 has exacerbated the situation by jeopardizing about 10 to 15% of production volumes in China, Spain, and Italy. However, Chinese companies resumed production in China in early March, resulting in a downgrade of 5 gigawatts for 2020 global installations, resulting in net 71 gigawatts of installations per latest forecasts. In fact, turbine manufacturers and suppliers can mitigate the impact by increasing manufacturing during the latter part of the year and reallocating supplies to other markets, such as India and Mexico. So let's look at the sustainability of these turbines. In fact, to manufacture just one turbine, they emit 11 grams of carbon dioxide per kilowatt hour of electricity. This is roughly 4 times less than solar, 44 times less than gas, and roughly 100 times less than coal. In fact, the amount of emissions here has everything to do with the manufacturing of the wind turbine rather than the operations. More specifically, the steel, aluminum, and resin used. This is a trend that continues to come up as we move towards a decarbonized society, where the majority of the decarbonization is now going to occur in the manufacturing of these green tech rather than the usage of them. When producing these wind turbines, the majority of the carbon emissions comes from the molding and casting process of iron and other ingots, as all of the required energy to cast these comes from the burning of fossil fuels, which generate the carbon dioxide. In fact, for a 2 megawatt turbine, this results in roughly 22,000 grams of CO2 produced. This can, however, decrease to roughly half the current amount of emissions by using an emission-free steel production format, such as the company H2 Green Steel, that uses a green hydrogen production method to manufacture steel. As in all my videos, I find it pretty difficult to completely decarbonize the entire manufacturing industry, as there's a lot of natural processes that just naturally emit CO2. But we can fill in these gaps with the effective carbon capture technology. So in summary, 80 turbines of 2 megawatts of capacity will produce 53 megawatts of electricity in 25 years. And in that time, it will only release 7 grams of carbon dioxide per kilowatt hour. On the other hand, the carbon dioxide produced by fossil fuels is 865 grams per kilowatt hour. That means that in 25 years of operation, it will release 45 million tons of carbon dioxide. To absorb that much carbon dioxide, 1,000 square kilometers of forests is required, which is the same territory as 3 grizzly bears. Overall, the wind turbine industry has experienced the largest amount of annual growth in 2020. Preventing 1.1 billion tons of carbon dioxide from being emitted from the atmosphere. Studies by the IRENA and the IEA shows that we need to install at least 180 gigawatts of power every year through 2025. With the world installing 94 gigawatts of power in 2020 and China making up roughly 71 gigawatts of that installation. Then over 280 gigawatts of power after 2030 is needed, which is roughly 3 times more than the amount produced in 2020. In conclusion, wind turbines are only one part of the renewable energy puzzle in order to solve our current climate change needs. And while we do have a large way to go and more scalability improvements to make, the positive impacts are already starting to be visible. Thank you again for watching this video. If you found it helpful, please show me down below with a like. And if you didn't like it at all, by all means, dislike. I'd be more than happy to hear your feedback on how I can make this channel much better. With that being said, content like this takes hours upon hours to make, probably dozens of hours if I was to count up. So any support I get, I would greatly appreciate it. Help out the YouTube algorithm. That is it for me. Thank you again for watching, and until next time, keep innovating. I'll see you in the next video. Goodbye.